We've learned the graphs of sine and cosine. Now we're going to look at the graph of tan. For the graph of tan, again, same idea that we did for sine and cosine. We're going to look at our unit circle and we're going to look at the axis family. So if I place all of my axis family on here, just like I've done before, then I'm going to go around and see what those values are on my pie plate. So tan of 0, well, that's 0. What happens at tan of pi over 2? It's undefined. So that shows up as a non-permissible value as an asymptote at pi over 2. It's also undefined at 3 pi over 2. And we're just introducing the graph of tan now, but once you start to graph tan, that'll be the first thing you're going to draw. The first thing you're going to draw is you're going to draw some asymptotes. You're actually going to also draw some in the negative direction. If you think about your angles going in the negative direction, negative pi over 2 is coterminal with 3 pi over 2. And so it will also be an asymptote. So we're going to have asymptotes, and they're going to keep on going. There's going to be asymptotes further and further along. But then if you look at your other values, at 0, at pi, at 2 pi, negative pi, tan is equal to 0 at all of those points. Now, what happens to a graph when there's asymptotes is your graph gets close to those asymptotes. So now the question is, well, what does it look like in between these? Which way is my graph going to be going? How could I figure that out? Well, if I go on my unit circle and I think about moving around, some values that would be easy to graph would be the pi over 4 family, because tan of pi over 4 is 1. So if tan of pi over 4 is 1, and I wanted to mark 1 and negative 1 on my graph here, where is pi over 4 along my x-axis? Well, pi over 4 is right between 0 and pi over 2. So I would know that there would be a point there at pi over 4. What's our next pi over 4 family member? 3 pi over 4. 3 pi over 4 is in quadrant 2. That's right between pi over 2 and pi. And tan of 3 pi over 4 is negative 1. Tan of 5 pi over 4 is 1, and tan of 7 pi over 4 is negative 1. What this allows us to see is if we want to graph our graph towards those asymptotes, you can see that your graph is going to look like this. And it's going to do that in every one of these sections. Usually what happens is after time, make that dot big enough so the graph goes through it. There we go. Usually after time, what you get used to is you say to yourself, well, the tan graph kind of looks like an x cubed graph, just a bunch of them repeated over and over and over again. It's not quite the same shape as an x cubed graph, but it's very similar in the way that it looks. So this is the graph of tan. And again, what we've shown here is what you would be expected to draw quickly. In your textbook, they have the graph of tan. I'm not really happy with some of the things. They've got extra lines in there. They've labeled things by pi over 3, which is, it's not useful for graphing tan. For graphing tan, you need your asymptotes at pi over 2 and 3 pi over 2. It's important to have your axes family on there because that's where it's equal to 0. And so the way that we graphed it, things were just easier to see. But there's some important things we need to highlight here. Unlike sine and cos, the period of tan is only pi. If you think how long does it take for it to repeat itself, well, from one asymptote to another, it repeats itself because it has that x cubed looking thing over and over again. What is the distance from pi over 2 to 3 pi over 2? That's halfway around your circle. And so the period of tan is pi. We have a bunch of asymptotes. We have asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. And you might notice, since one of our big ideas this year was tan is sine over cos, that pi over 2, 3 pi over 2, 7 pi over 2, 5 pi over 2, all those odd pi over 2's were the same place where cos was equal to 0. And when cos is equal to 0, you'd be dividing by 0, and dividing by 0 is not allowed, and that's how we've seen non-permissible values in the past. And when you've had graphs with asymptotes or holes, they always happen at non-permissible values. So our non-permissible values of tan are the same place where cos is equal to 0, and that fits with our big idea because sine is tan over cos. Tan is sine over cos. So if we wanted to say the domain of tan, okay, they've actually written it in an odd way here that doesn't really work mathematically. With saying n is an odd integer, we're going to write it the same way that we wrote it for cosine. And we wrote the odd numbers of pi over 2 for cosine in two different ways. So here's a reminder. One way is we wrote an odd number is 2k plus 1, because 2 times k makes it even. And if you have an even number and you add 1, you're going to get an odd number. And that's going to get multiplied by pi over 2, where k is an integer. That was one way that we wrote an odd number times pi over 2. The other way, so we would say for our domain x cannot equal all of those values. And another way that we could write our domain was to say the first one it can't equal, which is pi over 2, and then to think how far is it to go from one of these dotted green lines to the next one. From pi over 2 to 3 pi over 2, that distance is pi. And you could add or subtract pi as many times as you wanted. And that would be another way of writing the same thing. Now, our x-intercepts are exactly the same place where sine is equal to 0. And how did we write that last time? Well, it's pi, 2 pi, 3 pi, 4 pi. Those are all of our multiples of pi. So we could write that our zeros are just k pi, where k is an element of the integers. And finally, for tan, our range is everything.